Hi guys, it's your guy Olumide, and today we are going to be talking about a crucial problem solving technique that is used to solve some of the most complex data structure and algorithm problems. It is the backtracking problem solving technique. Imagine you are in a maze and you are at an intersection point whereby one route out of these three possible routes actually leads to the exit, but you don't really know which particular route leads to the exit, so you decided to try all possible routes one after the other, and then you decide to go for the first route, which is route A. Now, going through this passage, you come across another intersection point that actually breaks into two routes, two more routes, which is the route D and route E. So you decide to follow the route D. Now, upon following the route D, you see that it got you to the a dead end, right? And then you decide to backtrack to the second intersection point like this. So and therefore explore the other route, which is the route E. Now, exploring this route E, you also find out that it leads to a dead point. So you decided that okay, that means that this whole path right from route A actually leads to a dead end because it extends into two more routes, route D and route E, which both leads to a dead end. So you decide to backtrack back to the main intersection point, which is the first intersection point. And right here you are. So you decide to take the next possible route. Since you have explored route A, you decide to explore route B. So exploring route B now, you found out that it actually leads to the exits. Now, this brute force of testing every possible path, and backtracking upon failure is what we call backtracking. This is essentially backtracking, the process of testing every possible path one after the other. So, and whenever one leads to a dead end, you backtrack. So until you get to, and you try, after backtracking, you try another possible path. If it leads to a dead end, backtrack again and try another possible path until you actually found a way out. That is essentially how backtracking problem solving technique works. In backtracking, the state space tree can be created by considering, it's also called the decision tree, right? It can be created by considering all possible decisions that can be made at any point and at each point in the process. So this actually represents and essentially represent the state space tree for the maze scenario that we talked about here. So as you can see that we have the first intersection that leads into three routes, A, B and C, and then along the route A we have the second intersection that leads to two more routes, D and E, so which further leads to a dead end. So the state space tree actually gives us a good visualization of how decisions are made and of the solution space, right? I mean, for now, having this diagram and this visualization, we know that every solution space to the problem of the maze scenario is already included in this particular tree diagram, right? Because okay, we know we are going to start from the first intersection, and either we go into one of these three routes and then traverse downward up D and E, and then if we and since this actually leads to a dead end, we go back to the second intersection and back to the first intersection, and then we follow the other path, which is the route B, so which will lead to, and so it creates some sort of solution space, right? So, and it reduces ambiguity. So let's consider some common terminology. So we have the edges. Now, each edge represents a possible decision, move or action. So we say that these are edges, so it will actually represent a decision, a move from intersection 1 to either intersection 2, or to this exit, or to this dead end at C. So that's what edge represents. So the root node actually represents the initial state or position before any decisions are made. That's what we call the root node, the initial starting point, while the intermediate node actually represents partially completed states. Look at this intersection now. It actually represents a partially completed state or intermediate position, while the leaf node represents the complete or invalid solution. So as you can see that these are leaf nodes here, these are also leaf node. So any node that actually does not have link to any other node is a leaf node. That's the end node at that point, right? So all of these are leaf node, and it will either lead to a dead end or a successful complete solution. So like in this case, whereby this leaf node here leads to an exit, that's actually what we are trying to find, an exit. But you can see that this other leaf node here and here actually leads to a dead end. So those are the two possibilities for a leaf node. So a path actually from the root to any leaf node represents a sequence of decisions that leads to a complete or invalid solution. So as you can see, a path from this root node following the roots A to this second intersection, following down to root D, which actually leads to a dead end, actually is a wrong path, is an invalid path. So but it is a path, whereas a path from this intersection 1 and following down through the root B, which actually leads to an exit, is another path, even though is a complete and a right path. So having a good understanding of and trying to figure out and draw this state space tree or decision tree actually gave us a good understanding of how the backtracking algorithm works, and a good trying to figure out this state space tree is actually going to trying to figure out how to traverse this state space tree or a state space tree for any backtracking problem will actually lead us to essentially understanding which backtracking algorithm to use to solve the problem. So, and that simply means that if you can figure out how to traverse this particular state space tree, then you have essentially created logically you have created a backtracking algorithm to solve this problem, because it's all about understanding how to traverse this tree. So if we understand how to move from this first intersection to A and down to second intersection and to D, and then because we come across a dead end, how to backtrack again to E, and when we come across a dead end, how to backtrack again to this first intersection and go for this second route, definitely we already figure how to solve the problem and which algorithm to use. Now backtracking the search space tree is typically done using recursive DFS, the depth first search algorithm, whereby we try to recursively iterate through all possible paths along a tree or along a process. And now it involves a termination condition. So the algorithm is going to involve a termination condition whereby we define the condition that specifies when a path should end. So this condition should define when we found a valid or invalid solution. So this termination condition is what we have here, because I have the visual I have the code snippets for the backtracking algorithm. So you're gonna be having is an edge case, so let me say the best case. So it's just a way of terminating the recursion to prevent a loop, to prevent an infinite loop, right? So we have this termination condition that we actually that termination condition is gonna be placed there specifically for a leaf node. So don't forget that if you look at the backtracking, we always have a leaf node that will either end at a dead end or lead to a exit, right? So this termination condition will be placed at that point, so that it's gonna be able to process the state and return, so as to avoid an infinite loop. So the termination condition will specify when a path should end at the very leaf node, right? So this condition should define when we found a valid or invalid solution. So another core part of a backtracking algorithm is that a point whereby we iterate through decisions. We iterate through every possible decision at the current node. So imagine we are at this current intersection 2 now, or probably at this intersection 1. We want to iterate through all the possible solutions at this intersection 1, right? So, and that's what we do here, that for decision in every possible decision for that current state, what I want to do is I want to make that decision, mean that what, take that path. And by taking the path, what we are doing essentially is that what, we are making that decision and we are updating the current state accordingly, meaning that we are updating it to the fact that, okay, this particular path has been taken and the current state is no more here, is now currently here, or probably is now currently at this second intersection, right? So we make that decision and update the current state accordingly. Then what we want to do is that we want to recursively explore all paths that actually branch from this updated state by calling DFS on all possible by calling the DFS function on this particular state, so that we can explore all possible paths that branch out of the state. So it's simply by what, first of all we start at the root node, right? And then what we're gonna do is that we want to explore all possible paths, right? And as we make the decision of exploring the paths one after the other, what we wanna do is that first of all we want to update the states, so that the states of our environment, of our program, could be aware that now we have currently made a decision. So update the states that you have made the decision, then again explore all paths that branches from that path that you made and that you take, right? So exploring it now, so one after the other. So, and that's how we just keep on doing that. And then when we get to a dead end or a solution, we then backtrack again by undoing this decision that we made and reverting the states. So for decision in possible decisions, we make that decision, right? Then we call DFS on this particular state, so that we can explore all the other possible decisions that can be made from this new and current states. So, and after exploring all possible parts from that one, we want to undo this decision again by backtracking, right? So, and this is how we solve, this is how a backtracking algorithm logically and typically work. So now let's talk about when to use backtracking. Backtracking is useful when we need to explore all possible solutions to a problem. For example, if we need to find all possible ways to arrange items or generate all possible subsets, permutations or combinations, backtracking can help to identify every possible solutions. So now that's what backtracking is very good at, right? Probably want to perform permutation, so permutations of a strings, or different problems involving permutations, combinations, trying to check all possible subsets. We do use backtracking to solve problems like that. So let's talk about the real world example of permutation. We see that backtracking. Backtracking is essentially used in AI algorithm for games. So backtracking is used in AI algorithm for games like chess and Go to explore all possible moves and strategies. Imagine all these games like chess, like Go, and there are some other games, other mod gig games like that. I actually played some back then, and probably I'm starting to forget about them. But any game that actually involves you playing with the computer, you playing with artificial intelligence, actually involves backtracking. So, and what the essential need for that this particular problem solving techniques in such a game is that the program will use it to examine each possible moves. So it's gonna simulate the game's progression and evaluate the outcome. So it's like before the computer make its own decision and play its own part of the game, it's gonna simulate. Imagine something like Ludo, playing Ludo game. It's gonna simulate it and try every possible move, and then backtrack. Whenever you try one and you see that, oh, this one is gonna lead to a dead end, it backtracks again to try another part. So, and then it's explore all the game tree until it finds the optimal strategy, right? That's what actually happens. So it's gonna look into every possible part and then choose the best and optimal strategy to win. And that's why it seems the AI is kind of smarter than humans when we play games. So this is how and this is what backtracking entails. this is just a peripheral of what it entails, and we are going to be considering real-time DSA problem that involve backtracking problem solving techniques. So do watch out for more and for more of this in my subsequent videos. So the problem is going to involve include find all permutation, n queens, find all subsets, combination of some, funky part combinations, and then other related problems. Thank you. Do well to subscribe to my YouTube channel so you don't miss any of these problem solutions, right? The link is in the comment section, and kindly follow through and subscribe. Thanks.